Hello students, this is Miss Brihammar. This is 11.4 lesson where we are going to learn about the period of motion of a block spring system. This is the last lesson of this chapter. We are only going to deal with a so-called block spring system, and in the block spring system we are always going to have a wall to the left and the spring is attached to that wall, and the spring has a spring constant. The stronger that spring is, the higher that number is going to be, and the weaker this spring is, the lower that number is going to be. There's going to be a mass attached to it, which is in kilograms, and we are always going to assume that the table is smooth, meaning frictionless, so we ignore it. The important in what we are going to learn today is this red dashed line. This is called, the equilibrium position. That is when the spring is completely relaxed and it's just sitting there. Equilibrium position. Okay, here we go. So what we know so far from lesson 11.3 is that the force of a spring and a block is negative k times x. I know that the force is the restoring force in newtons, and if my spring is completely compressed, and here's my equilibrium, then my restoring force is that way. The restoring force is in love with equilibrium. So if I'm compressed, the restoring force is to the right, meaning the restoring force is going to be positive. If, however, the string is stretched, and here's my equilibrium, force wants to go back to equilibrium. In this case, it's pointing to the left, so the restoring force is going to be negative. K is the spring constant, and there is a little trick there, and that is that if the K value is negative, then the force is negative, okay? And vice versa. X is going to be the displacement of the block from the equilibrium line. Equilibrium line means that you have no displacement, so that's 0. If you're over on this side, then X is positive, and if you're over on this side, your displacement is going to be negative. In our case, this here means I am totally stretched, and if I'm over here, it means I am completely compressed. Kinetic energy ties into this, and it's the same old equation, 1/2 mv squared. Then comes the interesting question. When we have a block spring system, when do you have maximum velocity? When? Well, if you look at the equation, mass is mass. That doesn't change. But I'm going to have the greatest velocity where I have the greatest kinetic energy. Okay, kinetic energy goes up, velocity goes up. Where does that happen? At the equilibrium point. Imagine that you're sitting here at the equilibrium point on a string, and then I stretch you and I let you go. When I let you go, you're going to go swoosh over to this side, and you're going to be the fastest right there at the equilibrium point. Potential energy, we have always used with the equation mgh, but not for the block and spring system. For the block and spring system, we have a new equation. Potential energy is 1/2 kx squared. K is the spring constant, and x is how much you displaced. So when you have 0 displacement, meaning you're on the equilibrium, then you have no potential. Everything is kinetic. But if you are completely stretched or completely compressed, then you have maximum compression, maximum potential energy, sorry. Here's our new equation. The new equation is capital T, which I always leave a little bit tilted, and this is your period equation, period of oscillation. And the period of oscillation of a block and a spring is 2 pi multiplied by the radical m divided by k. M is the mass and k is the spring constant. Okay, make sure you write this down somewhere on your notes. Now, the period of oscillation has another equation. So which one are you going to use? The one I just showed you or the next one I'm going to show you? Well, it depends on what they're asking for and what units are given to you. So here is the equation from the previous slide where the period, which is measured in seconds, is 2 pi m over k rooted. And here's your second equation where the period of going back and forth is 1 over frequency. And you might recall that frequency is measured in hertz. So two equations giving you the same answer. So what is this period of oscillation that I keep talking about? Well, it's the time it takes to begin to swing back and forth, and come back to where you started. How much time it takes to make one complete cycle of back and forth, that is your period. So if your equilibrium line is here, and this is where I start, what is one cycle? One cycle is completely stretched, then passing equilibrium and being completely compressed, and then back to where you started. This here represents one cycle, this way, all compressed and back to where you started. That is one cycle, that is the period. How long did it take to do this? How many seconds did it take to do it? So, when we have a block on a spring, let's take a look at a picture what that would look like. So here we have our equilibrium point right there. There's your equilibrium. If the block sits right there, that means the spring is not compressed, it's not stretched, it is totally neutral. Here we are compressing, we are compressing, and we are extending. Compressing and extending. So if I start here on my equilibrium and I go to the right, then I pass as the equilibrium and I go to the left, and then I go back again. Oops, I went too far. If I go back again to equilibrium, guess what I just did? I did one period, which is one cycle, which is the period of oscillation in seconds. So take a look at this dude here. Now, do you think you can pinpoint where his equilibrium line is? Well, I'm going to put a little tick mark there. Maybe too early. Completely stretched. Okay, let me erase that. That was horrible. That was not good. Let's start over. So I'm going to put a, there was his maximum, and I think there is his total compression. So what is in the middle? That's x equals 0. That is your equilibrium point. Here is the same thing. This block is sitting at equilibrium, and he can stretch. The restoring force would be negative because the restoring force wants to go back to equilibrium, or he could come all the way over here and compress, and if he does that, then the restoring force is going to be positive because the restoring force always wants to go towards equilibrium. So here's a word problem, and we're going to use these three equations. And we have a spring, and it doesn't have a lot of mass on it, but I know the spring constant. Then we attach a 2 kilogram block to it. So I know the spring constant of the spring. That's a pretty strong spring. And we're going to put it in oscillation. We're going to make it go back and forth. And I'm going to stretch it. So when I stretch it to a maximum stretch, how far did I stretch it? Well, first of all, I know if I stretched him, I know my restoring force is going to be negative, and I know my displacement is positive because I stretched him. So we're going to use Hooke's law. Now, I want x. They gave me k, but I don't know the force. But I can go back and use this expression. F equals ma, and a is going to be due to gravity. So ma equals negative kx. If you isolate x, okay, here's the algebra, and plug in the numbers, and guess what? The block displays 0.01 meters. If you want to stop the video at this point, go over the calculations and see that you can get it. Now we're going to take the same system, but now I am going to compress it. So I'm going to push that spring and block to the left, and I pushed it 0.06 meters. Warning, it went to the left, so that's 0.06 meters. Now, I want you to calculate the period, and I want you to calculate the frequency of the block using this information. So I know K, I know the mass, and I know the displacement is negative. There's my negative. Okay, if I didn't catch that, my calculations would come out wrong. For B, calculate the period. I'm going to use this equation. 2 pi is 2 pi, the mass is 2.5, and the K value is 2.45. Go ahead and plug that into your calculators and see what you're getting. If you did it correctly, you got 0.635 seconds. That is the period of this system, meaning he's over here compressed, he's going to pass equilibrium, and he's going to come back to where we started. That whole thing took 0.635 seconds. Now you're asked to calculate the frequency, and I'm going to use this equation. I'm just going to press the inverse button of the period, because if t equals 1 over f, then f equals 1 over t. So you can just take 1 and divide it by our period. And if you do that, you are going to get 1.6 hertz. That is how many waves goes through in 1 second. How many waves are doing this oscillation in 1 second? Now again, stop this slide, go back and take a look at it, because this is the end of lesson 11.4 and we are at the end of chapter 11. So there is a PDF called PDF 11.4. It's pure calculations. It's 6 questions. Go ahead and do it and pay attention to the due dates. And on that note, we are done. Have a great day, guys. Bye-bye.